So today my plan was to talk a little bit more, well, actually a lot more about U-substitution as we go. It's kind of, so what I would say about U-substitution is when I am anti-differentiating something and it's not just a straightforward use the anti-power rule, the next thing I typically, well, I should say the next thing I typically do is try to simplify it. But if that doesn't work, then the next thing I typically look for is a U-substitution. That is always my first kind of, what can I try if I'm trying to integrate something? I will also point out that unlike taking a derivative, when you take a derivative, it's usually a straightforward process. You see a product, you do the product rule. You see a composition of functions, you use the chain rule. You see a quotient, right? The rules are very prescriptive. They're just telling you, you see this, you do this. With anti-differentiation, it's not always super straightforward. We definitely have clues that'll tell us what kind of method we should probably try. But sometimes we're going to try stuff and it's not going to work. So just be aware that as we learn more methods of integration / anti-differentiation, eventually you'll get to a point where you're going to have to try a thing and it might not work, and then you have to try another thing. Someone will probably often tell you, oh, you should try this. But sometimes on an exam, for example, someone might be like, okay, integrate this thing. And you might not know if you have to do a U-substitution or simplify it or use integration by parts. So just be aware that it is a process of trying things, and sometimes the things don't work. Okay, let's look at a couple more U-substitutions, and then we'll get into the trig stuff. So let's say we wanted to integrate something like this. Sure, let's say, I like that one too. Let's say we have 8y over the cube root of y squared plus 19 dy. And as far as we're concerned, I usually go horizontal. Okay, whatever. Fine. I'll change my orientation in a minute here. As long as I should say, it doesn't matter what variable we're using. The only thing that matters as far as integration is the variables in your antiderivative should match up with the d whatever over here. So if these are all y's, that better be a dy. If they're all x's, it better be a dx. If they're all u's, it better be a d. They have to match. Otherwise, it doesn't really make sense. So if they match, great. And I see a prime candidate for u. I'm going to let u equal y squared plus 19 for the usual reasons. The usual reasons. Yeah, okay. The reasons being reason one, actually, I should say reason two, that thing y squared plus 19 is stuck inside another function. It's stuck both in the denominator and, more importantly, in the cube root. Although being in the denominator is also a stuck place. You can't really get out of the denominator necessarily. But more importantly, now I'm going to say something, it's not going to be 100% true, but it's true enough. More importantly, the derivative of u is also in my integral. Now, that's not entirely 100% true, but it's true enough. Let's see what I mean by that. If I find the derivative here, du dy, which is going to equal 2y. Oh, and I guess I'll try and do it the way your teacher's doing, because they're definitely doing the thing when they solve for dy or d whatever. Here's what I want to point out. I don't exactly have 2y in my integral, but I don't really care, or more importantly, I can always adjust for any constant multiple I'm off by. So if I'm off by a multiple of 4 in this case, I can figure that out. If I'm off by a multiple of 13/2, I'm off by a multiple of pi. It doesn't matter what constant you're off by. As long as the powers work, we're good to go. So the fact that my du dy has a y to the first, and I have a y to the first over here, that is signaling to me that I am in a good spot. So I'm going to continue on, and I will do it the way you're doing in class, which is to isolate the dy. If you really want to do it weird, you can just like flip both sides over. I do not love that idea at all, but you could do that if you wanted to. I'm going to multiply both sides by dy, and then isolate the dy by dividing by 2y. So du over 2y is going to equal dy. Most of the time doing it this way is perfectly fine. Occasionally it'll run you into some issues, which we'll talk about when we get there. Excuse me. So now it's just a replacement game. I specifically, here's what I would recommend. If I'm doing a U-substitution in this particular way, I want you all really to only replace the dy with what it's equal to in this first step. I know we could do more, but I want you to be safe. So I'm going to rewrite this as just still 8y over the cube root of y squared plus 19 times, instead of dy, I'm going to write du over 2y. And the whole point of doing this part first is to see that something's going to cancel. You want to cancel whatever cancels before you move on. So we're going to cancel the y's. I know, and also I guess 8 over 2 is 4, sure, but that's not the important part. So I'm going to rewrite this now as the integral of, well, 8 divided by 2 is 4. And typically when we're doing these things, we often like to pull constant multiples out in front. That's just a pretty standard practice. So I could write 4 over the cube root of, well, I'm not going to write y squared plus 19 because now I'm continuing on. Y squared plus 19 is my u. So I'm going to write the cube root of u. But I would probably rather actually put the 4 out in front and write this as 4 times the antiderivative of 1 over the cube root of u. And I probably missed a golden opportunity there to do more simplification. But I just want to say, like, you can either write it like this or write it like this. We often are going to factor or pull out constant multiples when we can, because it just makes life simpler. Here we should definitely rewrite this as 4 times the antiderivative of u to the negative 1/3. So the idea of this process is that doing the u sub, right, replacing whatever we've decided to call u with u, is supposed to make this easier, right? Anti-differentiating u to the negative 1/3 is a straightforward anti-power rule. Whereas anti-differentiating 8y over the cube root of y squared plus 19 is not straightforward. It's really not easy to see how to do that. So then we do it, we get 4 times u to the, let's see, negative 1/3 plus 1 is positive 2/3. And then instead of dividing by 2/3, we're going to multiply by 3/2. Plus c. Right, once we have done the antiderivative, if it's again, if we're not talking about area, which we're definitely not talking about area yet, it's just an antiderivative, we're always going to throw on a plus c after we've done the antiderivative. And now we have to get back to the variable we started with. So if you're finding an antiderivative of a function, the antiderivative should have the same variable. So we're going to get, let's see, 4 times 3/2 is going to be 6. And u is going to be replaced with what u is equal to, which is y squared plus 19. To the 2/3 power. And that is our answer. I will also mention we're done, and you definitely should generally stop here. But if you wanted to check to see if your answer is correct, you could take the derivative of this. So just to point out that we did it the right way, if I take the derivative with respect to y of this expression, 6 times y squared plus 19 to the 2/3 power, the 6 multiple hangs out. I didn't write the plus c because I know the derivative of plus c is going to be 0. I guess I could write it. Okay, fine. Twist my arm. Okay, plus c. If I take the derivative of that, the 6 is going to hang out. I have some stuff to the 2/3 power. The derivative is going to be 2/3 times my stuff to the negative 1/3 power times the derivative of the stuff. And there we have it. I'm not going to simplify that further, but you can totally see we have 6 times 2/3, which is 4, times 2, which is 8. So we have 8y, and we have a y squared plus 19 to the negative 1/3, or divided by the cube root of y squared plus 19. So totally works. Not necessary to check this, but you can check it. Questions? Yeah. The 3/2 right here? Yeah. So what I did, I kind of skipped a step, and I said, when I'm gonna anti-differentiate this, I'm gonna get the 4 is gonna hang out. And when I do the anti-power rule, I'm gonna get, sorry, my 4's sometimes look like u's. I'll try to make them look different here. I get u to the negative 1/3 plus 1 divided by the same thing. But I don't want to write all that out. So what I'm going to do is I'm going to say, well, I know that negative 1/3 plus 3/3 is 2/3. And if I'm dividing by 2/3, that's the same as multiplying by the reciprocal, which is 3/2. So that's where that 3/2 is coming from. And you'll probably see your teacher do this as well, where it's going to be like, I know I'm going to divide by this fraction, but I'm just going to multiply by the reciprocal straight away. Other questions about this one? Okay. Yeah, we'll we're never not getting away from this. We're never getting away from this, which is to mean that U substitution is going to stay with you probably the rest of your 16 series mathematical career. It's never going away. You're always, I mean, maybe in 16C we get away from integration a little bit, we do some other stuff, but really, like if you're talking about finding an antiderivative or an integral, U sub is always in the back of your mind. And to be honest, it is the method you were hoping you get to use, because of all the things we learned about integration, this method is usually considered to be one of the easier ones. So I always hope, like, let's hope it's a U substitution. Things are going to work out great if it is. If it's not, then okay, others. So let's question, yeah. That's a big question. It's not, it's a fair question, but it's a big question. So I guess what I would say is that so let's actually look at another example and I'll kind of talk about how I'm thinking of it. So let's look at, I should think about that for a second. Okay, sure. So let's look at something like, let's go landscape here, which is the way I usually like to go. Sure, we can do that. Okay, let's say we had something like, sorry, I keep saying something like, let's do this. Sure, let's say we have the integral of, all right, let me make sure I don't screw this up with my numbers here. So let's say we've got x cubed plus, sorry, I'm braining it up over here. Oh, plus 6x squared plus 3x minus 4, all to the 5th power. And on top, what do I want to have? I want to have, sure, 9x squared. Don't fuck it up. Sorry, 1 sec. Plus 36x plus 9, I think. Ooh. Actually, I'm gonna change it. Sorry, I'm gonna change. It's gonna be the. So I'm gonna make it a little bit different. I see something I can make it a little bit better. Let's instead, I'm just gonna factor out a 9. So let's say instead we're gonna do the integral of x squared plus 4x plus 1 over x cubed plus 6x squared plus 3x minus 4 to the 5th power. Sorry, and you probably already wrote the other thing down. I apologize. So, but a lot of you are using tablets, so I don't feel that bad. Paper people, I feel bad. Okay, sorry. All right. Anyway, so how do I know I should do a U substitution here instead of not? Well, currently, our only other tool in our antiderivative toolkit is kind of just to simplify it. And I can't simplify that because, right, even if it was just a straightforward, like, so just as a kind of aside, even if I didn't have that power there, even if my integral was just x squared plus 4x plus 1 over x cubed minus 6x squared plus 3x minus 4, I still, sorry, I'm checking to make sure. Okay. Oh, that's a plus, sorry. I still can't simplify that, right? If you have a quotient and your denominator has more than one thing in it, it's not really simplifiable. So I'm kind of out of methods, right? I've looked at the one thing I know how to do. Can't do that. I can't simplify that. So then I fall back on my other method. Now, is it a good method to use here? Well, let's try and answer that question. So looking at this or at this, what would be the ideal choice for you here? The thing in the bottom or the thing in the top? The thing in the bottom, for a couple reasons. One, it's in the bottom, right? It is, or as I like to say, it's stuck in the bottom. There's no way of getting it out of it. The only way you can get this out of the bottom, you're not really getting out of the bottom, is to rewrite this as x squared plus 4x plus 1 times all that bottom stuff to the -1 power. It's still stuck in a place. We've just written it differently. So that's reason one.
Would it be the -5th power?
Oh, well, I was looking at this one over here, which doesn't have the 5th power, but you're right. If I was rewriting this one, you're totally correct. It would be x squared plus 4x plus 1 in parentheses times x cubed plus 6x squared plus 3x minus 4 all to the -5th power. Yes. So one reason we choose it's because it's stuck. The other more important reason is we choose that to be U because its derivative is present. Now, again, when I say its derivative is there, what I really mean is its derivative or a multiple of its derivative is there. A constant multiple, right? Not like an x multiple, a constant multiple. So you can't say like, if I had like x cubed plus 4x squared plus x, that would not be good. If I took the derivative of this, that would not be wonderful. I don't want x multiples. I want constant multiples. So let's take the derivative. Du dx is 3x squared plus 12x plus 3. And I notice, because I made up the problem so it worked out, that this looks like 3 times the top, right? 3 times x squared plus 3 times 4x plus 3 times 1. So I can see that I'm in a good spot because my derivative is a multiple of something that's already in my integral. So now I'm going to do it the way that you are doing it in class, which is to say I have du divided by all that equal to dx. Although personally, I would no. Get off my soapbox. I don't have to do it the way I want to do it. I should do it the way you guys are doing it in class. So I'm going to start replacing things. And again, if you're doing it this way, I highly recommend just replacing dx with this and not doing anything else in the first step. So here's my first step. I have this is equal to x squared plus 4x plus 1 over x cubed plus 6x squared plus 3x. You might want to replace stuff just because it's a pain in the butt to write all this. Times du over, now instead of writing 3 times x squared plus 12 times x plus 3, it probably would make sense to factor out a 3 from the bottom so I can see things are going to cancel more easily. So I'm going to do 3 times x squared plus 4x plus 1, because then it's a real straight shot to say, oh look, that divided by that is just 1. And now we can continue on with replacing all the other things with what they're equal to. So I'm going to rewrite this as, so I've got du on top, and that x cubed plus 6x squared plus 3x minus 4 is my u. So it's going to be u to the 5th on the bottom. Some people like to write du over u to the 5th. Some people would prefer to write 1 over u to the 5th du. But either way, you want to rewrite it. I don't care if it's written like this or like this. We need to rewrite it as u to the negative 5th du. I will stress that when you're doing this translation problem, we're translating from the language of our original variable x to the language of our new variable u. It has to be complete. This integral can't have any x's in it. It has to be just u's, no x's, or whatever your original variable is. If you've still got x's, you can't start anti-differentiating. But we've just got u's, so we're good to go. We're going to anti-differentiate. We're going to u to the negative 5 plus 1 is negative 4 over the new power, which is negative 4 plus c. And then question. What 3? Oh, you good question. Yeah, that 3. What 3? Yeah, so you can put it here, or I would probably bring it out in front as 1/3. Yeah, excellent point. The 3 is yes, the 3. Oh my gosh. There's a 1/3. And so then I have a 1/3 times u to the negative 4th over negative 4. Good, thank you. Good call. And then I would probably rewrite this as 1/3 times negative 1/4, or 1 over negative 4 is negative 1/12. And then my u is going to get replaced with what u is equal to. I'm going to take that and I'm going to stick it in right there, and I'm going to get x cubed plus 6x squared plus 3x minus 4 to the negative 4th plus a c. So I'm a fan of throwing all my constants or multiplying my constants together to make it simpler. I don't really want to write 1/3 times all this stuff to the negative 4th over negative 4. I would prefer to write 1/3 times negative 1/4 is negative 1/12. You could also write it as, you could bring this back down to the denominator if you prefer. I don't have a good intuition as to which way is a better way to write it, because there isn't, right? Like you could write this as blah. You can write it as negative 1 over 12 times all that stuff to the positive 4th power if you prefer having positive powers. I can't think of a good reason to do that, except that it's another way of writing. Yeah, someone else. Yeah, did Gabriella, did your question get answered? What happened to the 3? Yeah, hopefully it did. So we can write it like this. Or we can write it like this. Or probably some other terrible way as well. Okay. Don't thank me. Thank, what's your name? Maya. Thank Maya. Maya was on top of it. As I imagine everyone else was like, you're missing the 3. Okay. If you see me missing, don't hesitate to say something. All right. So like I said, we're definitely not going away from this, right? U-substitution should always be there in the back of your mind. So if you're integrating or anti-differentiating and you look at a thing and you can't just simplify it to make it nice, powers of X or powers of whatever variable, the next thing you want to try to think of is there a good choice for you for a U-substitution? That is usually where I go to next. And I'll have to go, I think it might be posted on Canvas. It might not be. I do have kind of a flowchart's not the best way to say it. I have a list of questions that I kind of ask myself as I go through, like, do I try this? Do I try this? So it's a little bit shorter for this class as compared to other classes because we learn less methods of integration in this class, but it's still viable. So I'll try and find that and post it so you guys can take a look or even bring some to class next time. Although you probably don't need it yet because I don't think we'll learn another method of integration before your next test. I don't think, but we'll see. Trig. So when it comes to trig, to be able to anti-differentiate, I should say, when it comes to math, calculus, if you want to be able to anti-differentiate, you have to be able to differentiate. So if you want to know how to find the antiderivative of trig things, you have to know the derivatives of trig things. So let's write them all down. There are 6 trig functions. We're going to write them all down. There's a couple nice patterns I'm going to point out along the way. So first and foremost, trig. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. There's a couple reasons for writing them in this specific order. One of them is that to write them this way, these are like your primary trig functions, sine, cosine, and tangent. And also writing this way reminds you that sine divided by cosine is equal to tangent. Kind of nice. It's not true that cosine divided by negative sine is equal to secant squared. Just point out, okay. And then we have the other 3 reciprocal functions. So the derivative of the reciprocal of sine, which is the derivative of cosecant of x, is negative cosecant of x times cotangent of x. The derivative of the reciprocal of cosine, which is secant of x, is equal to secant of x times tangent of x. And lastly, the derivative of the derivative of cotangent of x is equal to negative cosecant squared of x. Yeah, that works. And it is true that cosecant divided by secant is cotangent. It's kind of neat. Right. Wait. Yeah, that's right. Yeah. Okay. So a couple things to see here. Thing 1. The derivative of any co-function is negative. What are the co-functions, you ask? The ones that start with the word co, or the 2 letters co. Cosine, cosecant, cotangent. Those are the ones that are the co-functions, and their derivatives are always, at least they start off with the negative. All right, if it's more complicated than just cosecant, you might eventually have a chain rule thing that turns it positive, but at least at the very beginning, it has a negative derivative. There's something else I wanted to say here. Oh, and I guess then the other ones are positive, right? The derivative of any cofunction is negative, and the derivative of the other 3. There's no good name for the other 3. I keep trying to come up with one. The derivative of the non-co-functions, right? The non-co-functions are positive. I don't know why I wrote a question mark there. The statement, not a question. So that's worth noting. The other thing I'll point out, which is a little, I don't know, a little hand wavier, but still worthwhile, is maybe you haven't memorized all these, which is totally fine. Although you should memorize all of them. But maybe you're not good at memorizing stuff, because I certainly am not. You can cut down on how much you have to memorize if you look for a pattern, which is the following. So first of all, I'll say you should definitely know sine and cosine. Derivative of sine is cosine, derivative of cosine is negative sine. The antiderivatives are the opposite. The antiderivative of cosine is positive sine, The antiderivative of positive sine is negative cosine. Right, so they change the signs. We'll see that in a second here. But the rest of the four, you can kind of get away with just knowing this one and this one. Here's what I mean. So listen very carefully. The derivative of tangent of x is secant squared of x. I'm going to take that statement and just slap on a co in front of everything. So the derivative of tangent is secant squared. The derivative of cotangent is cosecant squared. And of course, it's negative because it's a cofunction. And the same thing works for this and this. The derivative of secant is secant times tangent. The derivative of cosecant is cosecant times cotangent. And of course, it's negative because it's a cofunction. It kind of works. It's what I've always done when I try. So like, I'm always like, okay, I know the derivative of secant is this, and then cosecant, okay. All right, great. It's negative cosecant cotangent. The other thing a student showed me one time that I think is, it really helped them when they were like taking a test, they would just write this down really quick on the front of the test before they took the test, was they would say, they would write down these two things. They would be, yeah, okay, they would write down tangent of x, right arrow, secant of x, left arrow, secant of x. So that the derivative of tangent is secant times secant, secant squared. The derivative of secant is secant times tangent. I thought it was clever. Like they just came up with it. Oh, cool. And then they did the same thing for cotangent and for cosecant. So cotangent of x, right arrow, negative cosecant of x, left arrow, cosecant of x. The derivative of cotangent of x is negative cosecant of x times cosecant of x, which is negative cosecant squared of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x, which is what I just said. There's no saying it differently. So those are a couple ways to know the derivatives of trig functions. I do recommend memorizing. What I've told students to do in the past is take a picture with your phone, make it the background of your phone. I have not for trig functions, but there was one time I was teaching a class and there were some things I was like, there were some logical equivalencies I was having to teach and I could not remember something, like it just wasn't sticking in my brain. I did that. I took a picture of it, made it the background of my phone, or maybe it was the lock screen, not the background, whatever. And every time I looked at my phone, I was like, oh, great. If P, then Q means the same as Q when, or there's some weird like P implies Q stuff that was not important. But anyway, I recommend doing it. It's a way to see the thing all the time and you'll eventually remember it. That said, now we're going to use all this to then talk about the antiderivatives. So let me make notes here for a second. Cool. Yeah. Yeah. So here's what I would say. Anything you know the derivative of, you know the antiderivative of that derivative. So we can make a whole list here, and I guess we will, of antiderivatives. So I'm looking at this. I'm saying, okay, well, the antiderivative of cosine of x should be positive sine of x plus c. The antiderivative of sine of x, I'm not going to say the antiderivative of negative sine of x because it's kind of atypical. I know the antiderivative of negative sine of x is positive cosine. So the antiderivative of positive sine is negative cosine of x. Yeah, and I'm going to say this too. I'm also going to say, since it comes up, sine and cosine have kind of a cycle of derivatives. So if you start with, say, like f of x equal to sine of x, and then start taking derivatives, f prime of x is cosine of x. The next derivative is negative sine of x. The next derivative is negative cosine of x. The next derivative gets you back to where you started at sine of x, and you can just keep on going. So this direction, going down the list, is differentiation or derivative. And if you start down here and you go up the list, that's antiderivatives. So the antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is positive cosine. The antiderivative of positive cosine is positive sine. This is useful for other things. Later on, when we talk about integration by parts, it is going to be nice to know that this derivatives of sine and or cosine have this kind of cyclical thing where they just keep going back on each other eventually. Let's write down the other 4 that we want to know. So we know the derivative of tangent is secant squared, so the antiderivative of secant squared is equal to positive tangent. Let's see. And I guess I kind of blew it because I was going to write them over here, but oh well, I didn't. So let's write the other 3 now. So then we know that the derivative of cosecant is negative cosecant cotangent. So the integral of cosecant of x cotangent of x is equal to negative cosecant of x plus c. Well, let's think about that. If we take the derivative of negative cosecant, we get negative cosecant times cotangent, which is positive cosecant cotangent. All right, a couple more. The integral of secant of x times tangent of x is equal to secant of x plus c. And lastly, the integral of, sorry, I forgot the last one here. What is it? Well, it's on my list, cosecant squared. Integral of cosecant squared of x dx is equal to negative cotangent of x. Let's see. So this is our kind of starting place for antiderivative trig function. Now, I will point out, nowhere on this list is the antiderivative of tangent, cotangent, secant, or cosecant. There are things we will probably get to eventually, but they do require a little more. I don't know what the word's I'm looking for. They require more. They're not just straightforward. There isn't a nice, necessarily easy way to just be like, oh yeah, the integral of tangent is this. Although we are going to find it today, I think. Questions about this so far? Okay. So let's look at some examples. Oh yeah, we should do that. Okay. So here's the thing I really want you to take to heart. Sometimes we're going to see that there's a U-substitution we can do, and we're just going to do it in our heads because it's straightforward enough. Specifically, like in the following example. I want to find the antiderivative of cosine of 6x. And I'm going to do the U-sub here, but I'm also going to tell you what happens. So let me ask you all, and this is where I typically think about it. When you take the derivative of something, a thing happens. Meaning if I took the derivative of cosine of 6x, I get something, I get negative sine of 6x, and then what would I multiply by? Right, the derivative of the inside, which specifically in this example is 6. A constant. So here's what's usually going to happen if you have something that's just a slight multiple of x inside your function. When you antidifferentiate, instead of multiplying by the derivative of that function, which is a constant, you're going to end up dividing by the antiderivative, by the derivative of that constant, the derivative of that inside, which is a constant. Sorry, my words get a little tricky here. So what I know is going to happen, and I'm going to say is going to happen, is that we're going to get, or we're almost going to get sine of 6x. The problem is we're not quite right. Let me ask you all, what's the derivative of sine of 6x? Or think about it at least. What's the derivative? So let's see, sine of some stuff. The derivative of sine of 6x would be cosine of 6x times 6. But I don't have a times 6 in the thing I'm antidifferentiating. So to account for that or adjust for that, I'm going to divide by 6 or multiply by 1/6. Because now if you take the derivative of this, you're going to get 1/6. In fact, let's just write it down. The derivative of 1/6 times sine of 6x is 1/6 hangs out. The derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff, which is 6. And those cancel. Which means that is the antiderivative of cosine of 6x because its derivative is equal to cosine of 6x. And of course, we have a plus c up here. So this is the short way of doing it. The longer way of doing it is saying, well, I have a U-substitution. There's only really one good choice for u here, and that's the stuff inside the trig function. So we're going to let u equal 6x. Then our du dx would equal, the derivative of 6x is just 6. So solving for dx, I get du over 6 equal to dx. And now you can kind of see, oh, that's where the division by 6 is going to come from. So then rewriting our antiderivative here, we get the antiderivative of dx is du over 6. I don't have to worry about any x's canceling because I don't have any x's in this little equation here. So my dx is going to become du over 6, and my cosine of 6x is going to become cosine of u. I'm going to pull out the 1/6 constant because I can. I should say 1/6 constant multiple. And then we're going to get the antiderivative cosine of u is, well, we're going to have the 1/6 times sine of u, which is going to be 1/6 times sine of 6x plus c. But the point of this is that I hope for you all that you get to a place where doing an integral like this or an integral like this is just like, oh yeah, I know I'm going to divide by 6. Let's look at a couple more examples. I'm speaking of which we're, yeah. So let's say I want to find, papers. I want to find a place to put my papers on this table. I don't have, okay. Let's say we want to find the antiderivative of secant squared of 3x. Well, I know the antiderivative of secant squared of x. Right? I know that the derivative of tangent of x is equal to secant squared of x. So if I'm looking for the function whose derivative is secant squared of 3x, well, if I'm integrating secant squared of some stuff, I'm going to get tangent of that stuff. But what do I need? I need to multiply by 1/3 or divide by 3, whatever you want to say. Right? You can write it like this, or you can write it as tangent of 3x divided by 3. Either way is correct. But yeah.
So if we get a question like this on the exam, do you have any idea at all if our professor wants us to?
I don't. I really don't. Yeah, that's a fair question, and I don't know how comfortable they are with letting you just be like, you can divide by that coefficient. So I don't have a good answer to that question. One thing I want to point out about this is it only works for constant multiples of x being your u. I can, okay, I'm gonna expand just a sec. It only works for linear functions of x being your u, meaning you could totally find the antiderivative of, sure, let's do this. Sorry, I had one. Secant of 10x plus 3 tangent of 10x plus 3. This is definitely going to be, well, the integral of secant of x tangent of x is secant of x. So the antiderivative of secant of stuff times tangent of stuff is going to be secant of that stuff divided by, well, not stuff, right, divided by 10. Okay, but I want to emphasize here, this only works if you are dividing by a constant, meaning you cannot do this. So this is a no-go. If I want to find the antiderivative of, say, cosine of x squared, I'm going to tell you it's not sine of your stuff divided by the derivative of your stuff. Not by a long shot. Because if you took the derivative of this, you'd have to start using the quotient rule. You don't have to here because your bottom is just a constant. So here, this, right, if you want to find the derivative of sine of x squared over 2x, you need the quotient rule. And you're definitely not going to get back to just cosine of x squared. You're going to get like 2x times cosine of x squared times 2x minus sine of x squared times 2 all over 2x quantity squared. That's definitely not cosine of x squared. Also, interesting fact, you can't antidifferentiate cosine of x squared. It is impossible. There is no function whose derivative is equal to cosine of x squared. Or more annoyingly, there is, and that's what it is. That's the antiderivative of cosine of x squared, written as the antiderivative of cosine. It's kind of terrible, but people literally do this. Like, there are functions that actually can't be, you can't find a nice antiderivative that looks like just regular functions added, multiplied, subtracted, divided together. And so sometimes they just write them as the antiderivative. The most famous one that you are probably aware of, even though you don't know it, is the integral of e to the negative x squared. And the reason you probably know it is because it's the bell-shaped curve in statistics. And we can't integrate that, but we definitely like to find the area under it because it comes up in stats a lot. So just something to be aware of when you're doing this kind of cool, what we like to call a mini U-substitution. where you could do a U sub, but you don't really have to. It only really works if the thing that would have been your U is a linear function of x, a nice multiple of x, maybe plus a constant. Okay, got 10 minutes. All right. Oh, there was something else I was going to say, which is if you're doing a U sub, there's one choice of U that you never want to make, which is you never want to let U equal x or U equal whatever your variable is. Because if you did that, all you would be doing is just rewriting the whole same thing except with a different letter. So I just want to point out that if I was trying to do like, I don't have a good example off the top of my head, but I was trying to do something like the integral of, now I'm totally blanking. Let's see, what can I do here? If I was doing like, I don't know, x times the square root of x squared plus 5, letting U equal x is not going to get you anywhere. I just want to point out, if you let U equal x, then your derivative is equal to 1. So du equals dx. And then I'm going to rewrite this. Okay, dx is du, x is u, and x is u. I didn't do anything. I mean, I changed the letter I was using in my integral, but I haven't really made any progress. So if you're doing U substitution, we never want to let U equal the variable we're using. I will also contrast this later on when we talk about integration by parts, where you're finding a U and a dv. I know they use U for different things. It's terrible. You sometimes do let U equal your variable then. So it's perfectly okay to let U equal x in integration by parts later on. It's really, really never going to get you anywhere to let U equal x in the U substitution. Okay. Let's look at a couple more things here because there's more trig stuff we want to talk about. Sorry, where'd you go? Where'd you go? One second. Let's see. Okay. Yeah. All right. So let's look at something like the antiderivative of cosecant squared of, I don't know, x divided by 7. And we could totally do this the short way because we know a function whose derivative is cosecant squared. I think, right? It's negative cotangent. So I'm thinking, oh, this is going to be negative cotangent of my stuff. What's the constant I need to divide by to make this work? Yeah, it's 1/7. Because right, this is really, if you prefer, you can think of this as negative cotangent of 1/7 times x. And so we need to divide this by 1/7, which is the same as multiplying it by 7. We have the plus c. So this would end up equaling, I'm going to write it as -7 times cotangent of x over 7 plus c. We can check by taking the derivative. The derivative of -7 times cotangent of, I am going to write this as 1/7 times x to make it easier to think about taking the derivative. The -7 multiple hangs out in front. The derivative of cotangent of some stuff is negative cosecant squared of that stuff. And then we use the chain rule and multiply by the derivative of that stuff. Derivative of 1/7 times x is just 1/7. The derivative of constant 0. And then, hey, look, the -7 times the -1 times the 1/7 just ends up being 1. So that's going to end up being 1 times cosecant squared of 1/7 x, or in other words, cosecant squared of x over 7. So we checked, right? The thing we think is the antiderivative ended up having a derivative that was the function we started with. So yes, it is the antiderivative. Cool. Yeah, let's do a couple more of these. More time. Okay, maybe 1 or 2 more. So let's say, we should do that. Yeah. Let's say I have the antiderivative of sine of x times cosine cubed x dx. So you have sine times cosine, or powers of sine and powers of cosine. Typically letting u equal one of those things is a good choice, meaning letting u equal sine or then u equal cosine. Here there is a superior choice. Sometimes there's a clear choice, sometimes there's no good choice. But here, there's definitely a best choice. So let me ask you all. Of these two things, u equal to sine of x potentially, or u equal to cosine of x potentially, which of these is stuck inside some other function? Sine or cosine? Cosine. What is happening to cosine? It's being, yeah. So it might be helpful to rewrite this as sine of x times cosine of x quantity cubed dx. So definitely, right? So I will say the first criteria is met by either one of these. If you let u equal sine, its derivative is cosine, which is definitely in there. If you let u equal cosine, its derivative is negative sine, which is essentially definitely in there. So those two things are kind of met either way. So then we go to our second criteria, which is that, well, all things being equal, we typically prefer to choose u to be the thing that's stuck inside another function. So we're going to make this choice here, not that choice there. Although that choice actually would work for this problem too. It just requires more work, which we should do less work. So u is cosine of x, and our derivative du dx is negative sine of x. So isolating dx like we do, du divided by negative sine of x is equal to dx. So that's going to go right there. So we're going to just rewrite our integral as sine of x times cosine of x cubed times du over negative. I might write this as -1 times sine of x, just so it's super clear to me what happens when I cancel the signs. So I'm going to cancel the sine of x's. And now I'm left with the integral of u cubed divided by -1 du. Dividing by -1 is the same as multiplying by -1. So let's just say we're multiplying by -1. And then we've got a du. And yeah, constant multiples, let's put them out in front of the integral. And now it's a power rule. So I get -1 times u to the 4th over 4 plus a constant. And then that's going to equal negative, let's see, u was cosine. So it's going to be cosine of x to the 4th power, or you can use the abbreviated notation cosine to the 4th of x all over 4 plus c. From the page I want, from the page I want. Let me hit you with one more just because it's super cool. Yeah, one more. But I feel like so yeah. So I feel like you all are pretty good to go on your homework assignment. Covered most of the types of things you'll see. But let me look at one more thing. I know it's 2:58. So I want to look at both, actually two more things really. So I want to look at the integral of tangent of x. And I also want to look at the integral of sine of x over cosine of x plus 9. Now let's actually do the second one first. So the second one, there's a good choice for you. What should I choose for you for the second one? Yeah. Now I want to point out, a lot of the time when you're picking u, sometimes you're like, well, I can just pick cosine of x. But typically, if you can pick your thing plus a constant, you always want to grab that constant along with it, because it's kind of, you're getting it for free, right? If I pick u equal to cosine of x plus 9, the plus 9 is not going to change the derivative at all, right? The derivative of 9 is 0. So when I find du dx, I'm going to get negative sine of x, end of story, plus 0. And then solving for dx, I'm going to get du over negative sine of x equal to dx. Since I'm low on time, I'm going to do it all at once, even though usually I wouldn't. So I'm going to write this as the integral of sine of x over u times my dx, which is du over negative sine of x. The sine of x is cancel. The -1 comes out in front. So I'm going to write this as -1 times the integral of 1 over u du. Oh, I haven't given you next time. I'll have to be next time. Okay. So what's the antiderivative of 1 over u? Yeah, that's all the absolute value of u plus c, and then we throw back in our u, which was cosine of x plus 9. So we get negative natural log of the absolute value of cosine of x plus 9 plus c. Next time, remind me if I don't say it. I'll tell you why you get an absolute value there, because there is a reason you get an absolute value there. It's not just because we want there to be one. It's because we actually need there to be one. We can definitely talk about that next time. We're out of time, so I'll just tell you all should figure this one out on your own. The integral of sine of x over cosine of x dx. It's extremely similar to the problem we just did. I'll even tell you the answer. But you should do the work on your own at some point. It ends up being negative natural log of the absolute value of cosine of x. Which I think you can probably see. All right. I have office hours over in the math drop-in room. Come see me if you want to see me. And I will see you all on Friday.